Okay, hello everyone. Today I welcome you to the part 4 of our graph machine learning series, and we would be looking at graph convolutions. So, like as always, we have the GitHub repo for this series. It's available here, and for the people on Zoom, I'll put it in the chat. And for this lecture, we'll open this notebook number 4, which has the name of today's date and then Graph ML Lecture 4. And once you click on this notebook, it will take you to this page on our repo, where if you click on this Open in Colab, it would open in Colab and then you will be able to access it. So I'll just copy the Colab link in the chat. Yeah, I've pasted the link in the chat, and yeah, once you are there, yeah, please let me know. And okay, before we start, the first thing we have to do, since this is the first time we'll be using Collab GPUs, so we go to runtime here in this runtime in the menu bar on Collab. We click here to say change runtime. So since I was working on this notebook, the T4 GPU is already selected for me. But let's say if you have opened it, then if it's showing CPU, then you change it to your T4 GPU and then say save. And once you have done this, click on the right side of the window which says this connect T4. Yeah, and yeah, so yeah, and once it is connected to T4, you'll see this yes or okay check mark here, and it will show you that okay, you are connected to the Google Compute Engine with the GPU backend. Okay, so now we'll start talking about graph convolution network. And since we are done with the GPU step, we'll get started now. So yeah, so why graph convolution networks we are talking in this lecture? Because they are an advanced model compared to the vanilla graph neural network we saw in the last tutorial. And we see that the convolution operation has been proposed by a lot of scientists in different domains. Let's say signal processing, we have this convolution operation, which is like a mathematical operator between two functions, where one function modifies the behavior of another function. And in the context of deep learning, this has been used in the convolutional neural networks for image processing, let's say image classification or image segmentation, where you have the sliding operator as a filter which convolutes with the image, the way the or you can say the pixel data in the image to produce some kind of feature representations in the next layer. And the mathematical representation, it looks complex, but it just that how the function g modifies the behavior of function f, and then produces some output function which can be termed as the convolution of these two functions. And in convolution neural networks, this operation helps us to like figure out where the edges are or some textures, or let's say if you're doing face detection, then these convolution operations are learned on the go by the network, and then that's when these are useful. In terms of graphs, since graph do not have a regular structure, we have to modify this approach. And and right now we have a very complex looking equation of graph convolution. Well, but as we go into the lecture, we'll break it down. So uh, in this function, let's just look at what it is right now. Then once I break it down, it would get more clear that what we are trying to do here. So this h of l plus 1 is the feature in layer l plus 1, and it is derived from features in the layer l. And then you can see there's like four different matrices. This d to the 1 by 2, which is where d is the degree matrix of the graph. A is the adjacency matrix, or you can say the modified adjacency matrix. Weight is the learnable weight matrix. and which I've provided here. So let's do a step-by-step breakdown here. So in the previous lecture, we looked at vanilla graph neural networks, which had the adjacency matrix getting multiplied to the feature matrix, which is a way of telling that there is an inherent graph structure in the nodes, and using that adjacency matrix, the model can learn it. So similarly, we have this adjacency matrix. The big change here in graph convolution is that we are adding this identity matrix. I can make it a bigger to, yeah, make it more clear. Yeah, we are adding this identity matrix in the original adjacency matrix. And what it does is the changes it makes to the original adjacency matrix is that it adds self connections now. So you can say that each node is connected to itself in a loop structure. And the next one is your this d tilde, which is the degree matrix of this new adjacency matrix, which is the row-wise sum of the adjacency matrix. And then h of L is the node features in layer L, and W of L is the weight matrix for layer L. So wherever this transformed features will get multiplied to the weights learned in this layer, and now we have this nonlinear activation function such as ReLU, like similar to all kinds of neural networks. And now let's step by step, let's break it down and see why this is necessary. So why we are adding and this identity matrix to the adjacency matrix. The concept is that adding the identity matrix allows for self loops, which allows the nodes to consider its own features along with its neighbors' features. This was not there in our vanilla graph neural network. In the previous lecture, we saw vanilla graph neural network. We were just doing the we are learning the new representation just based on the neighbors of the node. It was not considering itself. So that's why we have this modified adjacency matrix here. Yeah, the bigger difference comes between graph convolution networks and vanilla networks, vanilla graph neural networks, is that we are using this degree matrix here, which is the this matrix d tilde, which is the degree matrix of this modified adjacency matrix. And what it does is that so let's forget the under root term. We'll make it clear next, like why we have this d inverse broken down into two parts while normalizing the adjacency matrix. Just look at this point, that what this d matrix is doing. So this normalization, or dividing the adjacency matrix by the matrix D, is a way of telling that we would like to normalize the features by the degree. Because in vanilla graph neural networks, we saw that if a node has a higher degree, then it controls basically the feature representation learning for all the nodes. So, and then what happens is that nodes which do not have many connections, or higher degree, then basically they don't contribute much, which makes model less sensitive to. So yeah, so there was so when we do not have this kind of normalization, the model is sensitive to the node degree of the graph. But since now we are normalizing the node features by their degrees, we are saying that, okay, although there could be like high degree or low degree nodes in the graph, but the model should give equal importance to nodes irrespective of whether they have high degree or low degree. And that's why we divide the adjacency matrix by the degree matrix, and that's how this d inverse comes in. And yeah, and then we have this weight matrix, which the model actually learns to map feature from one layer to the another layer. Then we have this nonlinear activation function, which is standard among all kinds of neural networks. Okay, so how this comes together is that the normalized adjacency matrix in form of like d root multiplied by this modified adjacency matrix multiplied by the root d matrix effectively like aggregates and normalizes features from each node's neighbors. And then we have multiplication by the features, then we multiply it by the weight matrix, put the nonlinear activation function to get the output. Okay, so this is the main point here, that how does it compare with vanilla neural networks, vanilla graph neural networks. So we in the previous lecture, we saw that vanilla graph networks have this kind of formulation, that we have the adjacency matrix multiply with the feature matrix, then we have this learnable weight layer here. Now for GCNs, what we're doing is we're multiplying this D inverse here. And like I said, why we are doing this, because each node features are spread according to the adjacency matrix and then scaled, because now we are normalizing the contribution of each node by its degree. So if you don't divide it by the node degree, then the nodes which have higher degree will dominate in the feature aggregation process. But since we are normalizing it, we are now telling the model that each node, irrespective of the degree, has equal contribution to the learning. Okay. So yeah, ideally the form is just D inverse, but this approach was used by this paper, Kiff and Welling, I think 2017 or probably before that. And they break it down into like D root, square root of D. And why does it's that? Since this is it's symmetric. Yeah, so this product results in a symmetrically normalized adjacency matrix. And they claim that this provides us like we can avoid numerical instabilities and probably improve the training. So that's why they divided it into like two parts, where you have like the one matrix in the front and then the back. So this effectively calculates D inverse A, but in a different way. And so again, putting everything together, we have this generalized expression of a GCN layer, where we have D inverse multiplied by the matrix A, the adjacency matrix. Then we have the feature matrix from layer L multiplied by its weight matrix to produce the representations in the next layer. Okay. Yeah, and then GCN improve upon vanilla graph neural networks in several ways. That first one is this normalization function, where you multiply the D inverse. And why I'm repeating this again and again, because these are just like the two major improvements over vanilla graph neural networks as compared to graph convolution network. That irrespective of the node degree, so the nodes with higher degrees cannot dominate in the feature aggregation process, and that's why this normalization is required. And then you have the self connections, adding the identity matrix to matrix A to tell the model that, okay, you have to focus on your own features as well. And then you have the weight matrix, which was same, like for example, vanilla graph neural network or graph convolution network. You have the same matrix here. Yeah, to learn the features, which would you multiply these weights to the feature vectors in layer H or layer L to provide the feature vectors in layer L plus 1. And then we have different applications of graph convolution networks, and some of the more prominent ones are in social network analysis, for example, in detecting communities or learning network dynamics and recommendation systems, let's say movie recommendation or some other kind of recommendation. Mostly it's used in molecular chemistry. Let, for example, you want to predict molecular properties. For example, given a molecule, let's say you want to predict like what's the solubility, toxicity, and drug-like features. Can these molecules be used as drugs? So in that way, molecules can be modeled as graphs, and then you can have graph convolution networks build on them. And then you can also use them in computer vision, where you have non-grid like data, let's say point cloud or mesh structures, or mostly like 3D modeling, where you have a mesh, and that's where you can use it. Okay. And you may be wondering that why this is called a convolution, because in CNNs we have the feature or the kernels, which actually acts like convolutions over the image features and learn the weight matrix. But Here, even though the mechanism of standard convolution of operation is different, but there are some commonalities between the graph convolution operation here and the signal processing convolution, that they all use local information processing. Next one is feature extraction. And then we have the shared learnable filter, which means that we have that weight matrix, which is learned from the neighboring nodes of one particular node. And that's how you can say that, okay, this is like one kind of convolution uh, defined for graph networks. And then it's useful because it highlights the network's ability to perform tasks, different tasks in CNN, but it's adapted more for graphs which do not have an Euclidean structure, or they do not have like a sense of distance, like as an Euclidean distance between 2 points. And there's like a complex topology of different points appearing in a graph. So that's where it's useful. So now after the theory, you can look at some examples now. So we'll use the NX library to visualize some of the graphs and then do some operations on it. So we can start by having this adjacency matrix where there's like 4 nodes, and some of the nodes are connected to each other. So you can start. Yeah, so once you click on the cell, it will ask you to run the notebook. And then once you define this adjacency matrix here, we can go and use the networkx library to build a graph from this adjacency matrix. And then we can also number the nodes. So once we have this, we can have this one small graph with like 4 nodes and 4 edges, where node 1 has the degree 3, and then node 2 has only degree 1, which is because it's only connected to the node 1, and then the other 2 nodes are just have degree 2. So that's where we can define this degree matrix, which is just like a diagonal matrix of the summation of A. Yeah. So and how do we verify that this is the correct diagonal matrix? So if you look at the first element here in the diagonal, which is 3, which tells you that degree for the node degree for the node number 1 is 3. And we go back to the graph and see, okay, it's connected to 3 different nodes, and that's why it's degrees 1. And so on and so forth. Let's say, for example, the node number 4, it's connected to 2 nodes, node 3 and node 1, and that's why it degrees 2. Okay, now we can also calculate the inverse of D here. Yeah, so we can use this linear algebra function from NumPy, which is used to calculate node degree, and that's the inverse of the, yeah. And the way we add the adjacency matrix, the identity matrix to the adjacency matrix, is that you have this original adjacency matrix. We define a new identity matrix with dimension 4. Since we have 4 nodes, so and then we like to add the identity for each of the nodes. So we define this new matrix A dash, which basically what it does is that it just adds this identity matrix to the original adjacency matrix. And the difference is that initially we could see that, okay, here all the diagonal features are 0, but once we add this identity matrix, the diagonal features are 1, which now tells us that, okay, the nodes are connected to itself, and then we do the D dash. So now, since we'll have the node connected to each other, then we'll have this so the degree for each node has increased by 1 since we added that identity matrix. And yeah, and we can calculate the modified diagonal matrix here. You can see that, okay, it's all the diagonal elements are now increased by 1. We can calculate the inverse as well here. Okay, yeah, and then this is our normalization function, that now what we'd like to do is normalize the new adjacency matrix by the new diagonal matrix. So we just do a matrix multiplication of T inverse with A. And then this is the normalized adjacency matrix, because we have divided the original adjacency matrix, the modified adjacency matrix A dash divided by the degree matrix, which is same as saying that we multiply the inverse of D with A. And then that's how we have this. Yeah, so this is the normalized adjacency matrix here. And now you can work out some functions from our work out some examples from our previous tutorial. So for that, we need to install PyTorch geometric. So if you run the cell, it will take some time and then install torch geometric so that we can use the graph convolution function here. And for datasets, we'll use the same Quora and Facebook page-to-page dataset on which we have worked in tutorial 3. Yeah, so once it's installed, if you run the next cell, can import torch geometric and use the functions. Okay, yeah, and then now we import the Quora dataset here. Yeah, if you want to know more about these two datasets, it's there in tutorial 3. Yeah, like what these datasets are, and then what problems are defined on these datasets, what kind of class labels are there, so on and so forth. So yeah, and then we have this degree. So what we are doing here is that uh, like why do we even care about using graph convolutional network? Because it introduces two things. Like first is the degree normalization, or the normalization of adjacency matrix by degree. So we are trying to see if that really helps. So, and to do that, we would first like to know what's the degree distribution for this Quora dataset. So, and for that, we have the degrees uh, uh, calculated for the graph from the edge index. And once we store them into this variable numbers, we can plot them out. And let's see how the distribution looks like. So once we plot it, we see that the degree distribution, or the node degree distribution for this Quora graph, is heavily skewed. That although there's like there are like many nodes with very small degrees, but then there's like one or two nodes which have a very large degree, about like 168, I think. Yeah, so, and then I provided the explanation here that this distribution appears to be like an exponential, or like an where with a heavy tail, that like one neighbor has like, so there's like so many nodes with only one neighbor, like 485 nodes, but there's only one node which has 168 neighbors. So this is a good example where we would like to divide the adjacency matrix by the degree matrix, because there is an imbalance in degree. And now we can train a GCN, the graph convolutional network here. So we can import the GCN conf model layer from torch geometric. We define the accuracy similar to our previous tutorials. Okay, and now coming back to the model, like how it works is that we define this class GCN, where it has two layers of GCN, and then starts with some input layer, and then we have like the number of hidden features here. And then the next one, the dimension of hidden features are taken as an input, and then we have this out, and then you will get like logits as an output, and then we use log softmax because it's a multi-class classification problem for Quora dataset. Okay, so once we have this is pretty standard compared to the vanilla graph neural network from previous lecture. Then we all define like what loss function we need to use, what optimizer we need to use here, and then okay, for how many epochs we want to run this. Okay, once you get the output of the model, how do you backpropagate the loss here? Then once you have the backpropagation of the loss and calculate the gradients, then you want the optimizer to make a step and change the weights here. And then yeah, so and then we are keeping a track of how the training loss and training accuracy changes by each epoch, and also for validation. And once the model is trained, we would like to test it on the test set. So this is pretty standard for all kinds of networks developed in PyTorch. Okay, so once we define our network, we can actually call the class with our Quora dataset. So now we are using 16 is the number of nodes, not nodes, like the layer the number of nodes in that layer in GCN. And now you're saying that for each node in the next layer, you should learn an embedding of length 16. So now we start from 1433 and then we go to 16. So we'll learn this one matrix which takes 1433 features, and then the next layer it creates a feature vector of length 16 for each node. And then you have the second layer which takes this new features with dimension 16 and then produces each produces 7 classes. And that's how the number of classes are defined in the Cora dataset. Okay, once we have called this model, can actually train it for 100 epochs, and since we are using a GPU now, it should get trained really quickly. And now since the model is trained for 100 epochs, we can actually test it on our test data set in our Cora, and now we see that it's about like 79.77, and if you round it off, it's about like 80%. Same thing we can do with our Facebook page-to-page dataset. Yeah, and similarly, since it doesn't have any train or validation or test, we can define it on our own. What kind of train, validation, and test sets are there in Facebook page-to-page? We can do the same analysis of degrees, and once we plot this, uh, yeah, and why I took this example, because again, we see like a heavy skewed function. This is more skewed than the previous example that here we have 709, no, not 700, it's like, yeah, so there are like 1500 or so nodes, or about, let's say, 1000 nodes which have less degree, let's say 0 to 50 or like 70, but there is like one node which has 709 neighbors. So this tells us that it's heavily skewed, even more skewed than our Cora dataset. And this is a great example for graph convolution network, because we are now normalizing the adjacency matrix by the degree. So that, and then we expect this network to do better than our vanilla graph neural network. Okay, similar to previous examples, we call our GCN layer. Yes, and then we start with each node having a feature vector of 128, and in the next layer it's modified to a feature vector of length 16. Then we have in the second layer we have the feature input as 16 dimensional vector, and eventually we predict the classes for each node as given by the number of classes in the Facebook page-to-page dataset. We fit this dataset, and again, since we are using a GPU, it should pretty much train quickly. Okay, once it's trained, we can go and test this and see we get about like 91.5, 91.4%. And since we use the same examples for in our previous tutorial on vanilla graph neural network, and then the multi-layer perceptron, where we start with the baseline that even if the model doesn't know about any graph structure, what's the baseline, or what's the best model we can make using a multi-layer perceptron. And when we compare, we see that the values for MLP and vanilla GNN are derived from our previous tutorial based on Cora and Facebook page-to-page on the test set. So we achieved about 53% accuracy on MLP for Cora dataset. Vanilla GNN gave us 75, but GCN gave us 80%, or I think, what was that? Yeah, about like 79.7 or 80%. So this tells us that GCNs are powerful in terms of actually using the graph structure when normalized by the degree, so that they can learn better representations for these. And if you go back and look at the number of the weight matrix, it's actually same that in the second layer, we always use the 16 dimensional vector to represent the second layer for these. So in terms of weights, these three models are equivalent, but just by using the normalized adjacency matrix or the degree normalized adjacency matrix, we are able to get better results for these two data sets, the Quora and Facebook page to page. Okay, now we can extend this tutorial to the two other data sets, the CiteSeer and PubMed data set from tutorial 3 as well. So yeah, right now we are just like downloading these two data sets. And once it's done, since we have already defined the graph convolution network here in this cell, we can call that class directly in the next cell here. Now we are using a CiteSeer number of features. Again, same 16 the feature vector in the next layer, number of classes. We can also fit this for like 100 epochs. Okay, and then we print it. So it gave us like 67%. And then we again, you can write another GCN model for our PubMed data. Can quickly train this. Yeah, once it's trained, can test the PubMed GCN on the test set. We get about like 78%. And so, and then in the next cell, I provided like a model comparison. So once we have this, yeah. So this is a comparison of multilayer perceptron, vanilla GNN. Both are discussed in the previous tutorial, and then in this tutorial we are discussing the graph convolution network based on 4 data sets. And so if we compare across all 4 data sets and all 3 models, we observe that there's like a clear outperformance of GCNN, the graph convolution networks, as compared to vanilla GNN and MLP, as defined in this table, that GSNN performs a lot better than vanilla GNN and MLP. Okay, so these examples were all about classification. Yeah, so before we go to node regression, we have a regression problem instead of a classification problem. If you have any questions, yeah, please let me know. Okay, we can resume to the node regression problem. So like what regression is, probably you know that instead of like class labels, we are now trying to predict like a scalar value, and that could be like anything instead of class labels. And for that, we are using this Wikipedia network dataset. And since this is the first time we are using this Wikipedia network dataset, I have provided the explanation of what it is, so we can just quickly look at this dataset. So I provided the link. So if you click on like Wikipedia network dataset, it will take you to the original research paper from where this dataset is derived. And this network has 3 graphs inside it, and we'll just look at 2 graphs, or I think only 1 graph for today. And then for right now, we are looking at this graph for this organism called chameleon, and they have like around 2,200 nodes and some edges. And then the same thing, nodes and edges are defined for other animals as well. And what this graph is, so in these network, each node represents an article, like a Wikipedia article, and then each edge is like mutual links between articles. So this could be like so chameleon graph could contain all the nodes, which each node is an article, and they connect with each other because they all are some kind of article based on the organism chameleon. So that's why it's defined as one graph. And this is provided in PyTorch geometric. So we can use this Wikipedia network function to get the data from there. So once we have this, we can also mention the name, that okay, we are also looking at the chameleon dataset, and we also have to like split the nodes, where we are saying that okay, we have 200 nodes in the validation and 500 nodes in the test set, so that the remaining about around like 1,500 nodes are in the test set. Because if you like sum them up and then subtract them from the total number of nodes, you'll get about 1,500 nodes in the train set. Okay, we can extract the data here and then can just print some of the information. It will tell you that okay, so there are about 2277 nodes. Each node belongs to one of the classes, and number of unique features is around about 2000. And since you may, so yeah, I mentioned it all here that this data set has classes, but we are talking about regression. So what went wrong? So yeah, so the issue with this data set is that it indicates 5 classes, but since our objective is to perform node regression, not classification, we can look at the data set and how it was generated, and then I found out that uh, so the problem was actually about regression. It's just that it was converted into classification by binning the regression values into 5 classes and then treating each bin as a separate class. So that's like one way of converting a regression into a classification problem. But to get the actual regression values, you'll look at this Wikipedia dataset available from Stanford. And once we download it, we should be able to see this folder here in the file tab. And if we click here, we will see that, okay, it downloaded everything. So even if we are done with this tutorial, if you want to try the GCNNs to other models or other data sets, you can look at these files which contain the data set for other organisms such as crocodile and squirrels. Okay, so coming back to chameleon, we can have this target value, the regression value, which are the log of page visits. So each of these values is the log of how many page visits each article had in some year in 2018. Yeah, if you look at the details of the data set, you'll get this information. Okay, so now we can go back and look at what's the degree distribution for this chameleon data set. Okay, and then once we plot the degree distribution, we also observe that this is also skewed and the graph looks similar, like in a skewed exponential distribution. And this makes a good case for our graph convolution network problem, because we already looked at whenever there is a skew in the degree distribution, graph convolution networks can help, because we use a degree normalized adjacency matrix in the formulation of the layer transformation operation in graph convolution network. Okay, so next we can look at what's the degree distribution of our regressor variable. So once we plot it, you can say that, okay, so this is the degree the not degree, the regressor variable distribution. And since we are binning this, we can plot the targets as well, which comes from the original data set. So if you want to, let's say, convert this into a classification problem, you'll just say like, okay, I want to do, let's say, 5 bins, and then so that's how you can convert uh, the regression problem into a classification problem by binning those regression variables. But right now we are just working with the original log page count values. Okay, so before we go to GCNNs, we would like to set up a baseline for our model, and that's we do with the multi-layer perceptron, where we just consider each node as independent. We do not tell the model that there is an inherent graph structure. We treat each node as independent node, and given its features, can we say something about the log page counts? Okay, so here we have here I have a 2-layer ML multi-layer perceptron, where we have the input layer. I've defined a hidden layer, and then we have the output layer after the hidden layer. And since this is a regression problem, we do not do any kind of activation, just we work on the pure outputs called logits from this model. Since we are working on a regression problem, we have this mean squared error loss instead of a categorical cross entropy or a binary cross entropy, which is done in binary or multi-class classification problems. We have the Adam optimizer here, and then we put the model to train, define how many epochs we want to run, get the output from the model, calculate the loss based on the train masks. And one thing is important to mention here is that since graph datasets are connected to each other, we actually need to have this train, validation, and test mask, because if we don't use this, there is a possibility of data leak, that the data from your test set can get leaked to your train set because you're not looking at the connection between the nodes. So that's why we only calculate the loss, because this loss will get used by uh, the optimizer to change the weights. So that it's necessary to mention that, okay, we are just now looking at only the test set. Yeah, and we calculate the loss, we take the derivatives of the loss and this backward step. Based on the loss, you calculate the gradients and change the model weights using the optimizer every 20 epoch. This is like the standard procedure we are following for starting from tutorial 2, 3, and now in tutorial 4. For every 20 epochs, we print the training loss and validation loss. And then once we have the test function, we can actually calculate the loss and then predict the test metrics later. Okay, so once I run the MLP for node regression, yeah, and this is a step which I've introduced for the first time in all the lectures, that since we are using a GPU, we just need to make sure that the CUDA architecture is available to run these operations quickly. Because if not, then this operation, since these graphs are very big, it might take a while to run these. So it's always good to use GPUs for this purpose, even if it's for demonstration. and and then once we ask PyTorch if CUDA is available, and then it tells us that, okay, yes, CUDA is available. So yeah, so the only tricky part using GPUs is that you need to, before training, or you need to put all the data into GPU, or even you can do this into while training at every epoch. Since this is a bigger data set, but it's not very big, we can put all of the data set to GPU itself in the first go. Yeah, so once this data set is put to GPU, yeah, you can also verify this if you go to the Colab here and then see uh, the GPU RAM. So yeah, if you, before that it was just 0. Once you put the data to GPU RAM, it should show that, okay, some data has been put to GPU. Yeah, we can reformat the regression variable here so that it matches with the model output. We can use the MLP class defined above to define a multi-layer perceptron model, and then we'll fit it for like 200 epochs. Okay. Yeah, since we are using GPU, it went like just very quickly. I tried this on CPU, takes a while to train it to 200 epochs, and now we can test this on the test set of this and see if you go back to test function, it's actually working on the whole data set. But since we have defined a test mask here, so even if you pass the whole data set, it will only calculate the loss between the data points which, or the nodes which were present in the test set using this test mask here. Yeah, and once we calculate the test mask, we see that, okay, the loss, which was the mean squared error loss, is about 1.09. Now we can use the scikit-learn library here to get the some of the regression metrics out. Uh, uh, we get the output for all of the data. We use the mask to give us the final predictions for each page or each node in test set. Yeah, and then we need to put the torch tensor to CPU as well to calculate this. Like, this is the standard that once you calculate the output, you put it to CPU, and then you calculate the different errors or different loss functions. Yeah, and then we print everything. So based on the test set for the Wikipedia Chameleon dataset, we see that multi-layer perceptron gave us the mean squared error of 1.09, root mean squared error 1.04, and then these mean absolute error is 0.77. So this sets us a baseline that, yeah, so this is like the most easiest thing to do with this data set using a multi-layer perceptron. But now the question is, can we do better using a graph convolution network, which uses the degree normalized adjacency matrix and the graph structure for this data set? So what we'll do is call the GCNCon function from torch geometric, we'll define a 3-layer GCN just to change something from our previous example here. Rest everything remains the same, that you have the input layer, first layer, you have like two hidden layers. This is your first input layer, this is your second, the first hidden layer, this is your second hidden layer, and then you have that output layer here. And then we are having this linear layer to just use the logits or just the raw outputs of the model. We are not going to do any thresholding because this is a regression problem. And then we add a lot of like a activation function here, then a dropout layer after each GCN layer. Yeah, once we have this, the rest of the procedure is same. Calculate the output, calculate the loss, use backpropagation to do the gradient step, use the gradients to change the optimizer. Okay, once this is run, we can actually verify the shape that it matches with the output shape of our model for our regression variable. We can, yeah, so this one is a little bit different because now we are flattening it. And then we have the GCN defined here, more parameters compared to our MLP model. Now we put our data to our GPU and then train it for 200 epochs. Yeah, since we have a more number of parameters in GCN, it takes longer to train this as compared to our MLP. Okay, so now our GCN for our regression problem has been trained on 200 epochs, and then based on a test data set, the test function remains the same, as similar to what it was in the case of MLP, that although we have the output for all the data set, we only calculate the loss for the nodes available in the test set using the test masks here. Okay, and then once we have this, we get that the loss for GCN on this chameleon Wikipedia dataset is 0.588. Okay, so and then now similarly we can calculate all the metrics using the scikit-learn functions. And once we have this, we can see that the mean squared error for the GCN Wikipedia dataset is 0.588, root mean square is 0.76, and absolute error is 0.588. And now we can compare these values. Yeah, they are a little bit different because they differ from run to run, because I didn't set any deterministic functions in PyTorch, so they vary a little bit, but they don't differ a lot by a lot. So based on this analysis, we can see that we use the Wikipedia chameleon dataset and compared two models, the multi-layer perceptron model compared to our graph convolution network model. We have used the three metrics defined for regression, which is the mean squared error, root mean squared error, and then we are using the mean absolute error. And in regression, these metrics means that the lower these metrics are, the better the model is. And if we compare our GCN to the multi-layer perceptron model, you see that these three matrices are less as compared to the MLP, which tells us that GCN performs a lot better in case of node regression in the Wikipedia chameleon dataset as compared to the multi-layer perceptron. Yeah, that's it for today, guys. Yeah, thank you.